general relativity step by step. We talked about transporting a vector, or at least the components of a vector, around along a path, and I made the observation that this, if this is equal to 0, we've got what's called parallel transport, and I showed you a little picture that looks like a feather. Where's my feather picture? There it is. It doesn't look much like a feather, but it did on earlier versions. So, where are we? Let's go back to this one here. Let's pinch in just a little bit. So if the right-hand side, if this right-hand side here is equal to 0, so if dv, which way around am I doing? Gamma by d lambda plus, I'm just copying this equation here, v alpha di x beta, what am I writing? Di x beta by di lambda, Christoffel symbol, gamma alpha beta. What's that summed over? That's summed over alpha and beta, and gamma's free. If that equals 0, this is a property, I guess it's a joint property of the path and the vector v, which has got components v alpha, let's say, in a particular coordinate system. And last time I made heavy weather of the fact that if you were talking about a scalar, then it didn't matter. There's phi and there's phi dash. It didn't matter which path you were going along. So the question is, if we parallel transport a vector around the place, is it path independent? So what that amounts to is, if you've got a circular path here, so we go all the way around there, what that means is, if we've got a circular path, let me just go to red, then that means that if I walk along here, pointing my arm out in one particular direction, then I get back to where I start. There's no difference. And so, of course, what that means is it doesn't matter if I go along the path that way or that way, I get the same answer. So path independence means when you go around a closed loop, you get back to the same, your vector points in the same direction. That's the same magnitude as well. Now, of course, that's true on a flat plane. What colour am I on? No, I'm still on red. Let's go back to black. Here's my black. Now you imagine you're on the surface of the Earth. There's your equator. That's your North Pole. There's your South Pole. And here I am. There I am. And what am I going to do? There's the North Pole there. There's some sort of lines of latitude going along here. La 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 la. And there I am. And let's just say that I'm going to point a vector. I've got my hand and I'm going to point it straight towards the North Pole. And I'm going to walk along this path. I'm going to walk up to the North Pole, which is about there. I'm going to go down here, and then I'm going to go back there. What happens to my little vector? Well, there it is, and it's pointing towards the North Pole. There you go. And then it goes down here. When I get back down here, it's pointing along the equator. Those are not very good arrows. Those are not very good. I'm going to draw those again. In fact, I'm going to draw my path in red. That's my path. There's my path in red. Don't like that. I'm going to do it again. And then down there like that. And there's supposed to be little right angle changes there. And if you're worried about the right angle changing, screwing things up, don't be worried, because you can just round off that path if you really want to. So here's my vector, and it's pointing northwards. There, pointing along here. Pointing along here, pointing along here, pointing along here, pointing along here. Aha! It starts pointing towards the North Pole and ends up, when I get back along my sort of round path around the Earth, triangular path around the Earth, my vector has changed. It's got a very different orientation. So what that shows us is, I'll go back to black, parallel transport. Or actually, vector transport. Parallel transport is not path independent. On the surface of a sphere. We're which is quite interesting, really. Well, it's not, well, of course, what happens is you look at it and you say, well, of course what's happened is he's fooling around in three-dimensional space, and yet your little person is trapped on the two-dimensional surface of the sphere. It's because the sphere is embedded in a non-trivial geometric way into a higher dimensional space, which we can see because we are three-dimensional organisms. We've got a three-dimensional sense, whereas your little person here can't. And so things that look baffling to him are readily explainable to us because we've got access, in our perceptual system at least, to a third dimension. Now, it was the genius of Riemann and the genius of Einstein that made the observation that the space we live in may well have curvature in the same way that the surface of a sphere has curvature, but not necessarily embedded in a higher dimensional space. And I find this very, very difficult to comprehend. I have got the mathematical intuition to deal with it, but I don't really have the geometrical. Maybe it's not possible to have geometrical intuition about this kind of thing. However, this is what I regard as super, super genius, that we have got non-flat spaces which are not necessarily embedded in a higher dimensional space, in the same way that the sphere is embedded in R3. So I'm just going to leave that there as an example of parallel transport not being possible, or, well, being path dependent in a space which has got, and we'll quantify this later, of course, in a space which has got curvature. So I'm going to stop there.